Hi, good afternoon. So I was at the Melbourne conference on Tuesday, and I was having a bit of FOMO. I was wondering, should I have just spoken at Melbourne? Because they're having a great time. But I decided to check that there's this great open data set to see where would Lakehouse actually resonate. And that data set is Google Maps. And I think it's very clear that New South Wales is the place where I should be talking about Lakehouse. I need to get a few dad jokes out of the way, so this is one of them. So what I want to speak about today is Delta Lake, which is a key piece of technology that enables the Lakehouse. There are different pieces of technology. But before I can start on that, I just want to level set as to why we need a Lakehouse. What is a Lakehouse? Who's heard the term Lakehouse? Who's got a Lakehouse? Couple of people, all right, awesome. Okay, so when we, so at Databricks, when we think about data and the value that it brings, we sort of look at a continuum that looks something like this, right? So we're going from low value to high value data, and what's in red is about sort of looking at the past. What's in blue is really trying to predict for the future. And when we ask a lot of organizations, where are they? They tend to be somewhere in the red, aspiring to be blue. There are pockets doing blue. And why aren't they further up along? And there's this chasm that people find it really hard to cross, and this is what makes the data ecosystem really hard in their enterprise. So they'll have a great warehouse set up, but it's not built for ML and AI. So then you'll have data scientists who want to work on ML products or ML problems in a data lake. And what's basically happening is we're copying and shuttling data across systems. And while that's fine, maybe in theory, in a large enterprise, especially if you're somebody in governance, it drives people nuts. Not only we're copying data across, we're duplicating storage costs, and then there's governance and security risks associated with that. So the idea of a lakehouse is, what if we could actually align those two systems together, right? Have the best of data lake and data warehouse in one place, and meet all your use cases from being a data engineer, a data analyst, to being a data scientist, right? Working off the same data set, always working off the same source of truth, and governed the same as well. And so that's the Lakehouse. So to enable the Lakehouse vision, there's quite a few pieces to it, but one key piece is bringing data warehousing, sort of semantics, guarantees, governance on top of your data lake, right? If you've managed a data lake, you know it's fraught with a lot of risk. You don't really get to control what's in there, who's writing to it, who's reading from it, who's deleting from it. And so that's why we have Delta Lake, and I'll dig into the internals very shortly. And the idea of Delta Lake is let's look at it from the bottom up. So at the bottom, you've got your lake, where all your files are sitting in cloud storage of your choice. And then you layer on Delta Lake on top. So essentially, Delta Lake is like a protocol that sits on top of your data lake files to give you those data warehousing capabilities. And then you'll have readers and writers through it. So we'll have a rich ecosystem of readers and writers able to understand Delta Lake files, being able to query them, being able to write to them with ACID guarantees and so on. Is anyone here using Delta Lake at the moment? All right. So what I really want to spend time today is, because this is a data engineering talk, kind of talking about how it works under the hood, because in my day-to-day job, I don't get the luxury of doing that. So bear with me as we go into the messy details. So first off, this started from Databricks, but it is open source. It's part of the Linux Foundation, and there's a wide ecosystem of contributors there, and even Australian companies like Atlassian and Canva. So Delta Lake started in Databricks around 2017. The first version was released open source in 2019, in June 2019. So it's been 3 years since, and it's been an interesting 3 years because what basically happened was you had a rich set of features that were open source, but then there were also a lot of features that were just Databricks specific. So it was very exciting then in June that we announced that we're bringing everything together. So everything is going to be open source as of Delta Lake 2.0. 2.0, I think, is in experimental preview at the moment, so you can access it and use it. And that's why I thought now's a good time to talk about Delta Lake, because it's not something necessarily where you need to be using Databricks to get full value out of it. You can be using it in any ecosystem to get value. So the beauty of Delta Lake is probably the things in blue there, like it gives you ACID reliability on top of your data. So if a record writing process gets corrupted, that data won't be recorded as a fully completed transaction. So then you feel, when you query data, you know that you're querying good, valid data, right? We have audit logs, we have the ability to time travel, and so on. That's all well and good, but it's not useful if it doesn't give you the performance you're used to from your warehouses as well, right? So we spent a lot of time with the Delta Lake protocol as well to make sure it is a performant data storage format so that you're not paying any performance penalties. All right, so with about 12 minutes to go, I wanted to dig into some of my favorite bits. Now, I don't know if I'll get through everything, so if you follow that link or scan that QR code, you'll see the full notebook. You'll get a copy of this presentation, so you can look at these at your own leisure later on. Hopefully, I get through most of it. The examples use a sample data set from Kaggle. It's about 10 years old now, but it's a Stack Overflow competition. I like it for about 3 reasons. It's about 3.7 gigs, so it's a nice chunky data set. It's got about 3.3 million rows. And let's face it, none of us would be here if it wasn't for Stack Overflow, right? So if it goes down, we're all in trouble. So the first thing we want to do is essentially, with Delta Lake, is to create what we call a Delta table. So this is our table that's going to store data. And as an example here, I've got how you'd create a view from the CSV file and then materialize a table. So if we actually take a closer look, this should seem familiar to you, right? So we're just creating or replacing a table. We're using the keyword there, using Delta. So Delta will be our sort of protocol under the hood. I've set some table properties like change data feed, which hopefully I'll get to cover soon. And then a location, right? So the location is where will all our Delta Lake files sit, where will our logs sit on top as well. And then I've got a query to populate that table, right? So hopefully this is familiar to all of you. So this isn't, so using Delta doesn't have to be scary. Then once we query it, again, tabular, here we got a tabular example. So let's start digging into some of what helps bring like ACID reliability onto Delta Lake. So one is, if we start to look at the file structure, sorry, it might not be very readable here, but the first thing to note is that location I gave you, that's where all the data files and the log files will sit. The data files are persisted in Parquet format, so even though I ingested a CSV file, we choose Parquet as a performant columnar-based storage format. And then what you'll notice is at that top level, there's actually a directory called _delta log. And that's where all the delta logs sit, which will give us the ability to actually see what is complete data, and it gives us the ability to roll back in time as well. And I think it's important to also notice that these delta logs are co-located with your data, right? So what that means is if you were to move that storage bucket or you were to point a different analytics engine on top of it, all that metadata is there with the data, right? So you don't need a separate meta store to manage it and handle it. So it gives you the portability. So I'm going to go back. So what you'll notice here is we have a bunch of, just look at the JSON files. So the JSON files are essentially your log files with every transaction. So if I were to generate more transactions, in this case I just ran like 250 transactions, we'll see that you'll have more log files. So at the end of every transaction, you'll have a log file that sort of tells us what changed in the data, what new Parquet files did we add, and that's our source of truth as to what the state of the data is after that transaction. So if we were to look inside a log file, it's essentially a JSON file. You'll see some metadata in there as to things like, you know, what columns are we partitioned by, what's the schema, and so on. If we dig down further, we'll see something like this, which says, at this transaction, we added this Parquet file. So we probably inserted a few records. So we said at the end of this transaction, this was a new file that ends up in our bucket. Now, your Delta reader, so that agent that wants to query the bucket, if it sees that there are files that are not in the bucket that are not in the logs, it will actually ignore those files because we'll assume those files were maybe partially written or corrupted. If they weren't captured in the log, then they're not real, right? So here's an example of what happens after I've done a merge into command, so essentially like an upsert. What it's saying is it's removed a Parquet file from its records, its memory, because we've modified some data and then we've rewritten a new Parquet file, so that's what the add is doing, right? And why the remove and add is important is we're removing it from sort of our view of the current state of data, but we're still leaving the file in the bucket. And that's useful if we need to time travel to a previous version, so we have that data we can go back to, right? So as we move through those transaction logs, your reader would essentially list out the transaction logs and kind of replay those adds and removes to kind of understand what's the current state of the data and be able to read that for you. There's a stats column as well, which you might see. So this stats column is what allows us to be very efficient with querying. So we can do essentially file skipping, right? So if we were to look at one of these stats columns, it'll look something like this. So for example, here you'll see like min values. So for every column for this file, it'll tell me what are the minimum values. And similarly, we'll have a maximum values and how many nulls there are. So if our query is trying to filter by particular keys, instead of trying to load all the Parquet files into memory and start filtering them, with the Delta protocol, you could quickly scan these logs to actually understand which files have the data you want or don't have it. And so we can do some efficient file skipping, which just makes life a lot faster and easier. Something I won't have time to cover today, but we can also do Z ordering. So in my example, I showed some just simple partitioning. Z ordering is another way to just efficiently kind of lay out the files by columns or keys that you're typically like joining on or filtering on to again speed up query performance time. But that's probably maybe a talk topic for next year. Other things so before I jump into the other things that make Delta Lake quite impressive, so I think the way the log files is really the key, right? So the data that's contained within is what gives us the guarantees, the ability to play back, the ability to be very efficient with our queries. And so everything I show you after this is kind of built off those log patterns, right? Schema, evolution, and enforcement. So out of the box, remember I showed you the schema is part of the metadata there. So what's nice about it is if you're writing straight to Delta, using a Delta protocol, if there's anything you're trying to do that breaks or goes against the schema, then you get an error out of the box, right? So, which is great, and then we can go back. If we really want to add this new column, we can evolve the schema. Similarly, if I try and insert something where the types don't match, then we get errors coming out as well. We can add constraints to our tables as well. So again, these constraints are reflected in the logs. And again, if we try and insert anything that goes against the constraints, then those writes are blocked, right? So we get our data warehousing governance and assurance through mechanisms like this. So another feature with logs, where I told you sometimes you're playing them forward, the great thing is we can play them back as well. So we have the ability to time travel, and there's many solutions out there that offer time travel-like feature. I particularly like time travel just because I get then paid to use my favorite Back to the Future memes in my presentations. So we have a describe history function, and with that you can basically get a view of how did your table evolve over, and here for example I just said a limit 10, so what were the last 10 changes that happened. So again, we're taking those logs and kind of playing them backwards to understand the state of the tables. You can get some useful metadata there as well to understand what happened. We can then time travel, right? So we can time travel to a previous version by version number, or we can time travel even by timestamp. So we could say, show me how my table looked 24 hours ago, or 4 days ago, or 4 weeks ago. So this gives us, again, better assurance, governance, and auditability, right? So if something goes wrong with your data, if a pipeline breaks, we can try and figure out when did it happen, why did it happen. And even better, we can restore these tables back to a previous version, right? So remember I showed you how remove didn't actually delete the file, it just told us we removed it. If we need to roll back to a version where we need that file, then that's what loads up. All right, so we have also, related to that, something called change data feed, which allows us to propagate track changes to our data in a granular manner. So here, for example, I've updated a particular record. It's shown me the pre and post view of that record. And all I've really done is that tag 5 column. I've changed it from a value to null. So again, I get a bit of auditability into how the data is changing, when it changed. And we can also use this table changes meta table to track the change data and propagate it downstream as well. So that second bit of SQL code you see there, I'm saying, tell me since a particular timestamp every record that was deleted, and I actually want to delete those same records in another table. Right. So I'm actually surprised I got to this point at this quick time. So Delta Lake, all of it is open, soon to be very open. So 2.0 experimental preview, hopefully GA very soon. I think it's a great time to start looking at the protocol as it gets adopted more broadly. I've only touched upon a brief section of it. If you find it interesting, we could probably do more on it, maybe at a future DataEng meetup or this time next year. As I said, all the resources available at this link or QR code, so please knock yourself out. There's a lot of low-level implementation details as well if you're interested. All right, thank you very much.